Alright, this lesson is about logarithmic functions and their graphs. To start, we want to remember that a log is an inverse exponential function. So I've listed some things about exponential functions for the function y equals b to the x, b being base, x being exponent. Exponential functions pass through 0, 1 and 1, base. They have a domain of all real numbers. They have an asymptote at y equals 0 and only positive values of range, so y greater than 0. As a result, we can say these things about a log of base b, or x equals b to the y, which are equivalent forms. Again, remember that we're talking about an inverse. 0, 1 would be equivalent with 1, 0 in a log. 1 base would be equivalent with base, 1. If the domain is all reals, I would say the range is all reals for a log. And likewise, I would substitute what I said about range for domain of a log. I can only take positive input values into the log, which is called the argument of the log, the thing that you're taking the log of. If I have a horizontal asymptote, I would now have a vertical asymptote. So let's plot these side by side. If b is greater than 1, I'm going to have a graph that looks like this as an example. So here's y equals 2 to the x, a value of b greater than 1. Considering what I know about inverses, then I'm going to make a vertical asymptote. I'm going to plot 1, 0. I'm going to plot base, 1. I'm going to be asymptotic to the vertical axis and go out like this, and I'm going to write y equals log base 2 of x. Because it's an inverse, it's a reflection over y equals x. Now let's look what happens when the base is between 0 and 1. You'll recall that that applies to things like radioactivity and half-life and so on. So the function decreases as I progress positively in x, still has a horizontal asymptote at y equals 0. Again, I'm going to inverse the point, so 0, 1 is 1, 0. 1, half would be half, 1. Negative 1, 2 would be 2, negative 1. I'm going to make a vertical asymptote again, be asymptotic to that graph, and I'm going to curve out this way. This one's a little bit more confusing than the other one. So this would be log base 1/2 of x. You may want to pause and just consider what I've talked about and review that a bit before we move on. Now, logarithms give the exponent on a base that's the same as the log base, that is equal to the log argument. So if I have an exponential function y equals b to the x, the inverse of that can be written x equals b exponent y. The other way that's more commonly written is y equals log base b of x. Now notice that the y is the exponent. Okay, so what was the exponent on the exponential is now the result or the output. The input is the output, right? And the thing that I put into the log is the result that I used to get with an exponential. That's the nature of an inverse. So keep that in mind, and if logs ever seem confusing, revert back to what you know about exponentials and then apply the inverse concept. Alright, some things you might be asked to do. These problems here you're asked to write in an equivalent form. That's another way of saying write an exponential as a log or a log as an exponential. Okay, looking at example 1, I see a base 2, so I will write base 2. Alright, I see an exponent 3, so I will equate this to 3, because remember, logs give an exponent. And the result that I used to get is the input or domain now, the thing I'm taking the log of, or the argument. So log base 2 of 8 equals 3. Maybe pause at this moment, try the other problems, and then come back and see how you've done compared to mine. Okay, here are the solutions for the other three. The exponential base becomes the log base. The thing that's the result of the exponential is what the argument of the log is, what I take the log of. And the exponent that I had before is the result I get. Now, with when I begin with a logarithm, I'm doing the exact process in reverse. When I see log base 3, I write a power of base 3. The log gives an exponent, so I write that as an exponent, and that's equivalent to the argument. Okay, and you can check the equivalence of these statements and that they actually make sense forward and backwards. Another type of question you can be asked. Use the definition of a log to evaluate each. So, in this problem, I've got log base 7 with the argument of 1 over 49. I'm trying to figure out what that equals. Maybe I'll write equals x. Let's write an equivalent statement. When I see a log base 7, I write an exponential of base 7, or a power with base 7. Logs give an exponent, so let's write x in the exponent place. This is equivalent to 1 over 49. So, what I want to do now is think about how I can rewrite 49 with a base of 7. So that's going to be 7 squared, and the 1 over is a reciprocal, so negative, which leads me to negative 2 is what that log base 7 of 1 over 49 equals. Pause and try these next two on your own. Okay, hopefully you were successful there. Compare your answers to mine. In each case, you'll notice that the thing I'm trying to evaluate that I don't know, I've chosen to assign it to x, an unknown that I'm trying to solve for. Then I'm rewriting the logs as equivalent exponentials in each case. After that, I'm trying to make the bases the same and match up the exponents. Okay, we'll move on. Now, the next thing I wanted to relay is the notion that the properties of log function graphs can be found or determined by thinking about exponential graphs and the concept of inverse, as well as possibly transformation properties if necessary. So here are a couple of functions. This one should say y equals. And what I'm asked to do is figure out information about the domain. Now, the base of an exponential has to be greater than 0, and it cannot equal 1. These are properties of an exponential. So looking at the first one, that means x has to be greater than 0, and x cannot equal 1. Now the argument of a log, the input to a log is the output of an exponential. Exponentials never have values that are 0 or negative, or another way to say it is that they always must be positive. So that leads me to saying, in this case, that the domain or the argument of the log has to be positive. And so in this case, x is greater than negative 5. Now, we've got several different restrictions, and I've got to compile these together and take the most restrictive case. So greater than 0 looks like this. Not equal to 1 looks like this. And greater than negative 5 looks like this. These are the three different situations that I've got to match up, and I can only use the parts that agree with each other. So you can see that the first case is not acceptable for negative values, so I can't use that. The second and third case allow x to be 0, but the first doesn't, so I can't use that. All three agree that I can use values between 0 and 1. I can't use 1, and all three agree that I can use values more than 1. So, taken all together, I would say this, that x is greater than 0, less than 1, or x is greater than 1. Alright, pause and try the next one, see how you do. Alright, that one's a little bit more challenging. We want the base to be positive, the base not equal to 1, leading to these two domain restrictions. Also the argument greater than 0 leading to this domain restriction, which I showed on a number line, and I want the overlapping parts. No good in this area, can't use 1/4, good in this region between quarter and half, can't use half, and good in the region up to 3. So there's your domain. Alright, using inverses, you could get different questions such as these ones. You're told 3, 7 is a point on the exponential graph with base b. What's a point on y equals log base b of x? Well, you reverse x and y. It's as simple as that. And next, here is an exponential function, and I would like you to sketch it. I'd also like you to find the inverse of it and sketch that. Let's look at the inverse first. The inverse function, when I see y, I will write x. When I see x, I will write y. I will isolate the exponential. Now at this point, I'll write it as a log. I see base 3, So I will write log base 3. The exponent is what the log is equal to, and so the third component is the argument of the log. Lastly, isolating for y would equal log base 3 of x minus 2 plus 1. Now, try sketching the exponential. That should be relatively easy. Then I'd like you to think of the inverse property and write the log, and then check your result with me after you've done that. All right, these are the results. In the case of the exponential, you'll see that I have a translation 2 up, so the horizontal asymptote rather is at y equals 2. Similarly, I will have x equals 2 as a vertical asymptote for the logarithm. Okay, I didn't write that down. I should define that. X equals 2. There we go. When I substitute 1 in, I get 5 as a result, so therefore when I have 5 substituted in, I'll get 1 as a result. Let's try that here. Put 5 in this place. 5 minus 2 is 3. Log base 3 of 3 is 1. Add 1, get 2. Pardon me. Let's see what else I want to say about this. When I put 0 in, I get 2 and a third. So the inverse of that can be plotted for the logarithm. The domain of the exponential is all reals, so the range of the log function is also going to be all reals. Okay. I think that's about it for this lesson. So you may want to review some of these things again to make sure they're all clear for you. And I will do some log law properties on the next video, which you'll also want to watch soon.